Hi, everyone. Imagine standing in the heart of London, surrounded by towering skyscrapers and the iconic red double-decker buses. Beneath your feet, however, lies a hidden world, an intricate geological landscape that determines how we build, expand, and sustain our underground transport system. Today, I will take you through an analysis of air quality variations across London. Then, we will explore the geology of London and the necessary geophysical techniques to ensure safe and efficient tunneling for a new underground. Air pollution in London varies significantly depending on location and pollutant type. Nitrogen dioxide and nitrogen oxides are highest in central London. These pollutants are primarily caused by vehicle emissions, making congestion zones the most affected areas. Fine particulate matter is widespread, with concentrations peaking in construction, heavy and industrial zones. On the other hand, ozone levels tend to be higher in suburban and rural areas. Unlike nitrogen dioxide and particulate matter, ozone is not directly emitted, but forms through photochemical reactions in the atmosphere. This means that while central London suffers from the highest direct emissions, outer boroughs experience increased ozone levels due to pollution dispersion. Compared to the rest of the UK, London records some of the highest nitrogen dioxide and 2.5 levels, mainly due to its dense traffic and industrial activity. However, rural areas outside London often see higher ozone concentrations due to the lower nitrogen oxides emissions, which would otherwise break ozone down. While air quality monitoring provides valuable insights, publicly available data comes with certain limitations. Monitoring stations are unevenly distributed, meaning some areas have less reliable data than others. Additionally, weather changes and seasonal variations can cause short-term pollution fluctuations that models may not fully capture. Building a new underground line can significantly reduce road traffic emissions by shifting commuters from cars and buses to clean. Expanding the network into underserved areas would encourage more people to use public transit, helping to lower nitrogen dioxide and particulate matter levels. Additionally, when considering the construction of a new underground line, it is essential to identify the locations of existing metro lines in London and determine which areas are qualified. I collected 4 types of air quality data from existing London underground stations and generated new London air quality distribution maps. As can be seen in these 4 maps, the darker the color, the more polluted the air. Therefore, the new underground lines can choose in these dark color areas. This can increase public transportation in these areas, thereby reducing pollution. Next, we need to consider London's geological features. According to the references, London clay was found to be one of the most suitable areas for excavated underground lines. Beneath the London clay lies the Lambeth Group, a variable formation of sands, clays, and silts that reaches up to 30 meters in thickness. This layer presents challenges due to its heterogeneous nature, requiring additional reinforcement during excavation. Further down, we encounter the Danette Sand Formation, a fine, weak sand that is highly permeable and demands careful groundwater management. Finally, at depths exceeding 100 meters, we reach the Chalk Group, which serves as the bedrock of London. While the chalk is strong, it is also highly porous and can contain significant groundwater, necessitating extensive dewatering measures before construction. From here, you can also see the depths and arrangement of different formations. However, uncertainties still exist, particularly in formations like the Lambeth Group, where the composition can change over short distances. To reduce these uncertainties, we must integrate additional geophysical surveys. Seismic reflection surveys can provide high-resolution imaging of subsurface layers, helping to detect faults and discontinuities. Electrical resistivity tomography can be used to map variations in rock and soil properties, highlighting areas of high water content that could affect stability. Borehole logging and core sampling offer direct insights into underground materials, allowing engineers to confirm geological predictions before full-scale excavation begins. But the composition of the Lambeth Group, found beneath the London clay in some areas, leads variations in strength and stability. Tunneling through this formation requires extensive reinforcements and careful management of groundwater. Granite, sand, and chalk formations located even deeper and are highly permeable, meaning that large volumes of groundwater must be managed during excavation. These conditions necessitate advanced dewatering techniques and ground stabilization measures to increase the complexity and cost of tunnel construction. River terrace deposits and alluvium, often found in surface-level layers, are another challenge due to their loose and unconsolidated nature. To avoid geological hazards like faults, unstable layers, and groundwater issues, advanced geophysical techniques must be used. Seismic reflection surveys help identify faults and variations in rock density to ensure tunnel stability. Ground-penetrating radar detects voids, weak zones, and hidden structures, while electrical resistivity tomography maps water-saturated formations to assess groundwater risk. Gravity and magnetic surveys reveal subsurface structures that may impact tunnel alignment. By integrating these techniques, we can reduce uncertainties in subsurface models and improve construction planning for a new underground line. In addition to this, in order to protect the ecology and not damage the greenery, we should avoid the vegetation cover and forest part of this map when choosing an address. Also, the selected address must not be in the flood zone on this map. By analyzing air quality data, pollution sources, land use patterns, and geological conditions, we can make informed decisions about where to expand London's underground network. Prioritizing areas with high pollution and stable geology ensures an expansion that benefits both the environment and commuters. With strategic planning, advanced geophysical surveys, and a focus on sustainability, we can design an underground network that reduces congestions and secures a cleaner future for London.